filter them out. Let me say, I do have 5 minutes, perfect. Let me say a few words about the niobium films that we've grown on sea sapphire and on borosilicate. I'm particularly excited about the borosilicate because it's a completely amorphous piece of glass that we've managed to grow a niobium crystal on. The sea sapphire shows the same trend, by the way. RRR goes up when you heat things, same thing with the glass. And it's interesting that the RRR values of 30 on borosilicate are higher than typical values that were quoted in the literature 10 years ago for the best thin films of niobium on A sapphire. So I think we've come a ways here. If you look at the pole figures again, you see polycrystalline behavior, twin symmetry here, twins, all gone at the high temperature and the high RRR. Just a single intense peak right in the center. So the texture, if you will, in this film is being washed out, and it's becoming more like a monocrystal. And if you look at the same data on borosilicate, they're also quite exciting, even though they're preliminary. If you look at the poor RRR, low temperature, and contrast that with the higher RRR, higher temperature, look first of all at the 110 peak. The intensity goes up here, which already suggests higher crystallinity. But then look at this sort of perspective picture here of the pole figure. See this rather fat peak in the middle? Look at what happens to it when you've ordered the crystal a bit more. And then these side lobes are also getting a little more coherent. Now this isn't as nice, obviously, as the niobium 110 single crystal structure we saw on A sapphire or on MgO. But I'll remind you that this is crystallinity we're seeing on a completely amorphous substrate. Now, if we bias this substrate, could we do even better? That's the next step. And it would obviously lead to being able to do something on aluminum if that made sense. This is not worth dwelling on because I suspect that Anne-Marie will show more of these kinds of data, so I'll just skip through it. This is just to show you that the SIC facility does allow us, in this case it was one of our samples on copper, and you do a BCS fit to it and you can deduce certain parameters. But the reason why I showed this on copper is before I get to this conclusion, since I hope I have 2 minutes left. One, that's long enough. That's long enough. I do want to share with you, this is just TC, is something we did over a year ago now, is when we put niobium on copper, and it was prompted by Genfa's comment. So at the coffee break, I had to come and throw these 2 slides in that I hadn't intended to. We put niobium on copper using CED, and the film thickness in that case was less than a micron. And the grains we saw were 50 microns in size. So what you see is EBSD of the bare copper, first of all. This is an 80 micron scale here. And you see these grains, you see the size, and then this is the niobium film on that copper. And it basically lays down rather large grains that are not unlike the grains on the substrate. It is faithfully picking up the grain information from what it's landing on. And again here, you see 110, this pale lime green color. It's pretty much there everywhere in that grain. So that's really all I wanted to share with you. And indeed, even on the copper, we found that when we heated the substrate to 300, we got a rather uniform 110 crystallinity everywhere and a nice Kikuchi pattern. But at the lower temperature, it was relatively poor with no Kikuchi pattern. Now I'm down to the last 12 seconds. So I'll just come back and use those to conclude. And I don't need to say anything, you can all read. Thank you very much.